we did not use to have such a problem. So starting saying that, I wish you can accept this cartoon with me. This is myself as a petroleum engineer and later on reservoir engineer. We are not free. We are tied into the other disciplines that we need to speak and understand their language. The link between the other disciplines and the reservoir and the petroleum engineers is data. So whatever they give us, we have to understand how they got it, what level of accuracy in this data, and where can use this data to get our mission accomplished as should be. So it's our responsibility to ensure that oil production is sustained. And we are talking about a plateau. And plateau means constant rate over a long time. So we have to ensure that the target production rate is always accomplished. Doing that, we have to be on the same level of understanding those disciplines, which we are working very close to them, and they are working very close to us. So the mission is a driven objective. We have objective to achieve, and this objective is driving us to accomplish the mission. The mission here, as I'm mentioning in those bullets, is mainly to explore, develop, produce, and process the produced hydrocarbons, sustain production plateau at lowest operating cost, and upgrade the reservoir development whenever is needed. Excuse me. So when I say sustain production plateau, I mean, if we are producing 50,000 barrels a day, we have to ensure that those 50,000 barrels a day can be produced for a long time. Losing production means that we have to spend the money for operations to rectify this problem and bring out the production back. So upgrading the case of enhanced oil recovery. At one time, we have to look how to better enhance the recovery from those reservoirs. So this is the big title of the company's mission that we are taking responsibility of. It's mainly a responsibility of the reservoir engineer and the petroleum engineer. The other supporting teams, drilling, workover, engineering, construction, production operations, they are supporting to bring that oil to surface. And we have to manage how can we keep this oil sustainable for a long time. So the mission will start, as I'm showing here, by spending money, facilities, more money is spent. And by the end, when we get that oil production to surface and they store it and start exporting, this is the time we are feeling the value of money we have spent, because we are bringing some more money, more and more money coming back. So this is the investment of the company. We are driven by objective. The objective is to ensure that the production is sustained and the target export is achieved. As usually, this is a quick start of what we are doing. We start with the seismic, and the geologists are looking at play or prospect that way you can drill. You shoot seismic lines, you shoot 3D seismic, 1D seismic, 2D seismic, whatever seismic acquisition is done. We have to be involved in understanding how this shooting is done and how this could affect the reservoir, and how we could provide data that help interpreting, processing, and interpreting and understanding the reservoir, because the reservoir is rock and fluids and pressures based on the compressibility of rock and the fluid pressure. So seismic people would need this data in order to be able to process and interpret the seismic data they receive. The communication, link between us and the geophysicist. As well, when we drill a well, we are targeting this nice reservoir here, and we are eager to understand how this fluid distribution is vertically and laterally. So once we are in a picture of having such beautiful saturation profiles, telling us that we have that much oil vertically and laterally distributed, we would be able to model it. The old days, we had to use the mud logging engineer that he can investigate the cuttings and find out if there could be a reservoir during drilling, so he can stop drilling and test, and sometimes run open hole logs if necessary. Sometimes run casing and cement it, and the production test it if we find it's a must. But in most cases, it's along the hour. This mud logging is providing data about the reservoir and the formation we are drilling through. So when we run logs after that, after reaching TD, it's not necessarily that we could see good saturation profile, because the mud in the well would invade and mask this saturation profile. This is why mud logging is one of the key elements to identify presence of hydrocarbons and alarm the sign of testing requirements. The saturation profile, as we can see here, is needed in order to map the development or the proven oil pool. We have that thickness, we have this area, so we can decide on the number of wells that need to be drilled in order to be in business and produce what we are looking for. It can be staged development, it can be one go development, it can whatever the strategy would call for, we can embark on the development of this field based on the most important, this saturation profile. This is the problem of the low resistivity pay. If I don't have this saturation profile, I'm not in business anymore. So confirmation of what we have, we can embark on running a formation tester to identify the different phases of fluids, gas, oil, water, where the contacts are, more data gathering to better understand this exploration well. If it is conclusive, if it is proven oil, or it is a fake, or it is anything can call for abandonment, like the wording low resistivity pay. Low resistivity pay management, they cannot explain it more than how much it can produce. And this will tell me that I have that long column of oil, that long column of gas, and this is my contact that can help me mimicking the picture of this saturation here. Production testing will give me all the feasible data that I need to produce at surface. Pressure data about the reservoir. So I'm capturing all the information needed in order to model this field. So if you have good reserves, you can sustain production for a long time. If you have little bit small reserves, you find you are shooting a production, and then it will drop and you lose production for after some time. And this is the problem of low resistivity pay. Low resistivity pay means that you don't have that much production to sustain it. So you can drive a picture, you can draw this picture of the reservoir, identify where the reservoir rock types, identify your capillary pressures, mimic a 3D picture of the reservoir that can tell you this is the structure, this is the oil pool, this is the gas cap, this is the bottom water, and this is the area that you can safely develop with whatever number of wells. So you include the geological model together with the fluid data and the fluid displacement data to come out with dynamic models that can mimic the dynamics of the reservoir while while the reservoir on production or injection. Once we do this, we can investigate the possible development options. You can go for whatever pressure support scheme, peripheral, or pattern development, whatever, because you are investigating the optimum method of developing this field in order to achieve ultimate recovery out of whatever is stored in the reservoir. This all is controlled by the saturation profile. Management would decide if you can go for fast cash flow, if you can go for middle plateau, or you can go for a low plateau that you can sustain production for a long time, and everyone will give you a recovery. So if you are shooting for cash flow, you lose recovery soon, and so on. So these sensitivity cases are investigated by the reservoir simulation engineer, who depends mainly on how good he could mimic the saturation of this oil pool laterally and vertically, because he is sure that there is an oil that can be produced to surface. So you started drilling, you fix the production facilities, and we are in business. This business is billions of dollars. This high expenditure depends, as I keep repeating, on how good a saturation profile is discovered. You have a saturation profile, you are in business. If you don't have a saturation profile, there is no way you can mimic whatever existing in a reservoir. So what is the problem of this low resistivity pay here? As you can see here, the resistivity, there is no saturation profile in comparison to this conventional. This is normal profile. Normally, we can produce a profile versus depth. We can identify where is the dry oil production, where is the transition zone, where is the contact. But here, you have no idea on how this saturation profile could be, in spite of this high production rate at zero water cut. Does it make sense? Can anyone believe that this is a 5,000 barrels a day producing formation with such very high water saturation? No one can believe it. There is something wrong about interpreting this 5,000 barrels a day. The doubt about this saturation profile, the resistivity, is controlled because we know the tool, the physics of the tool, and we know what might be there during drilling. So the anomalies of the anomaly we are looking at today and trying to understand and solve is how we can interpret a low resistivity pay reservoir. Experience it from the high reported production tested rates without any details of production testing technique, without any gas or oil saturation profiles, no definition of producing intervals, no definition of the producing development area, no volumetric figures about the discovered oil or gas. If you put yourself in the office of your manager after discovering such a reservoir and you don't like it, can you sell this concession? There is no way you can sell such concession, even if it tested 10,000 barrels a day, if you don't have a figure of how much oil in place it holds. So we are not in a business if we don't have such a profile of data. If you check the reported cases in carbonate formation reservoirs, true resistivity less than 1 ohm meter. So calculated saturation 85 to 100% using Archie, and they still could produce 1,500 to 5,500 stock tank barrels. And the surprise is zero water cut. Very low resistivity, very good porosity, very good production rate, and zero water cut. Even the saturation by Archie is almost 100%. Sandstone, you find similar, 2,600 barrels of oil per day, say more than 70% water saturation, and zero water cut. 25 million of gas, 3.4 millions of gas. The NMR that some people reported, this high water cut was attributed to micro porosity, that holding immobile water. Can you imagine if you have micro porosity of this reservoir holding immobile water, what would be the level of the average log porosity? And this is one of the input to volumetric calculations of the oil in place. Cases from carbonate sandstone reservoirs, we noticed the reported figures advised us that there was good match between core porosity, which is the effective porosity, and the log porosity. If I believe that this was true, then I would have to ask myself where the micro porosity was that holding this immobile water. So this is the case here, as you can see in the resistivity and porosity, they are matching. Neutron and the density porosity are matching. Quite clean gamma ray. And even though the disappointing here that you cannot construct a saturation profile. Would you consider this a proven discovery? And if it is proven discovery because you tested 5,000 barrels a day, would you consider it as commercially proven? You as a reservoir engineer or petroleum engineer have to ask yourself always when you face such a situation, because by the end you are taking responsibility of delivering production to surface and to the market. So the decision, if you consider this is an exploration well, and you have such picture, what decision you can take? We run a production test regardless of what we are seeing here, if it is wet or do we have some hydrocarbons that we are not seeing? Or we consider it a wet zone and quit the location. In most cases, the owners would not go for spending more money unless they have quite evidence of good hydrocarbon saturation. In this one, if there is no evidence, they will not go for testing. Unless you have a strong indication from mud logging that you have high counts of gas, you have some oil shows from the cuttings. But to depend only on TD wireline logging results, you would be in a mess. So we have to bring all the pieces of the puzzle together in order to understand what could be there. These are some examples, reservoir A, B, C, D, and surprisingly that you see 100% water saturation and the formation fluid gradient from formation tester showing oil, light oil, 0.227, heavy oil, 0.38, heavy oil, 0.33, almost fresh water, 0.45. This is less saline than the seawater. And they all reported 100% water saturation. And you can see on the other side, very high rate with zero water cut. 4,800 barrels a day, 2,000 barrels a day, 5,500 barrels a day, and no drop of water was reported. As a reservoir engineer, I would have to question all this data, how it comes that we have such oil with zero water cut and this high saturation. And in the case of MDT, which I trust because I know the pressure points are seeing the continuous flow phase, and the continuous flow phase would be related to whatever it reflects as gradient. So if it is oil, it is oil. There is no way that you can miss interpreting the pressure points. Instead of saying formation water of 0.48, it could tell you 0.27 oil. There is no way. But you can get some change in the gradient that could be close to whatever you are trying to understand. Coring, the core operations indicated shows of oil in 2 and 3 wells. The one other well was not cored. So if you bring all this information together, you have to ask, what was the problem? What happened that could change the nature? So natural conditions, we know exactly what should be. And when we interfere in this condition, we can change it because we are drilling. So what we know and what we don't know is based on what we have as surface facilities and drilled wells, but data captured from the reservoir itself as rock material, as logs, as production data, as pressure data. This all will give us the pieces of puzzle, pieces of puzzle that we have to understand the uncertainty level of the reservoir. And we can decide on what needs to be done in order to ensure that mission is achievable. So how much we know about this reservoir here is controlled by the amount of data and the quality of data. And this is your responsibility as a reservoir engineer, as I am myself as a petroleum engineer or reservoir engineer. I have to find out what is the data available, and these data are captured.
Bonsoir délégué. Je vais voir comment on fait coup, je fais coup. Oui.
Does anyone have a question? Okay, so this data is our source to mimic the condition of the reservoir. Lithology, we are talking about huge changes of the formation from being clean to complex to dirty, whatever. These all are wording. You can word it, you can write it in a text, but when you take it to the simulation model, you have to convert it into numbers. And unfortunately, there is no numbers that can bring the dirtiness of these formations into the simulation model. But it's good to understand that this is the type of reservoir rock we are dealing with, because this by the end can help explaining why I am seeing the low resistivity pay. The reservoir rock typing, you can see changes from micro to macro, the very small, tiny flow conduits to big enough high permeable rocks. Then 3 types of porosity, the macro and the meso and the micro. I'm not seeing this all, but I'm seeing the total porosity by the log. And this is the one everyone is using in modeling and using in calculating how much oil in place. So I wouldn't care about the display, the split between macros and the meso and the micro. If it's 10%, 50%, whatever it is. But when you come and tell me that this low resistivity pay is attributed to the micropores that has immobile water, and this micropores is part of the 20%, 23% of porous by logs, then I would have to imagine the split between this micro and the macro, because this macro would be dominant, meaning that the macro could be few percent and this one would be very high percentage. I'm trusting the number, the porosity by logs, because it's logged in every well using the same technique, using the same physics. So I have no doubt, but I started doubting the definitions here if I don't have the source of explaining why this is the main contributor to the phenomena we are looking at. The same way we are calculating. Naturally, we have oil-water matrix, and this is the oil is calculated based on how much water we can calculate from Archie equation. It's a simple physics. It does not lie. It does not cheat. And inside all this one, we have the irreducible and the free. It's a marginal. You can say irreducible is 20%, 25%, 15%. It doesn't matter, because by the end, we still have the model to control this one using the tuning process. But when we introduce to drill, we are introducing not filtrate. We are disturbing the nature. The natural condition of the reservoir rock is disturbed by the mud filtrate while drilling. So how far this mud filtrate could displace oil away from the drilled hole, this is the problem controlled by the drilling operations. So I'm as a petroleum engineer or reservoir engineer, I have to be on top of the drilling operations in order to control the mud weight while drilling and avoid mud filtration going deep into the formation. You can see it here. If it is natural, it's not invaded. And while drilling, you are seeing some mud going deep. And after pulling out of ore and running wireline logs at TD, the invasion has gone deeper and deeper. We have what we call today as logging while drilling, which is an advantage to avoid this invasion effect. But not every company is using it because of budget limitation. And the H tool, you can see it from very few inches up to 2 meters or 3 meters. The induction log can see very deep, and lateral log can see up to 150 centimeters. But if you have deep invasion, it could go and mask the depth of investigation of this tool, and instead of seeing it through resistivity of the formation, you could see the invasion of mud affecting the saturation profile. So the problem definition of the low resistivity is related to the recorded resistivity by logs. It's very low. It could be down to 1 ohm meter. And the water saturation calculated from Archie would be almost 100%. This used to be interpreted during the old days because in exploration, well, you are not spending that much time and money to find out behind the problem against one. So used to see this wet zone, they quit the location. If you don't have oil or saturation profile, you don't have a discovery. So if the geologist or driller or whoever witnessing the job come out and say that you tested 5,000 barrels a day, zero water cut in a reservoir that has a resistivity less than 1 ohm meter, what would you say? We have a commercially proven discovery, or it is nonsense? So it's a difficult decision for management if you are telling them such low resistivity pay. They always need to have something that they can tell money can be explained as production. But one well, you don't know where it can drill another well, where you can add perforations, how many wells you will be needed. There is no data that you can decide on development. So factor affecting the low resistivity pay reported everywhere, and if you are still, because we are dealing with formation, the formation is known, the external part is known. So if you combine all this, you should be able to find out the conditions leading to this low resistivity pay phenomena. We have static conditions related to the reservoir and the properties of the rock. So you can call conductive minerals, presence of conductive minerals, microporosity, holding this immobile water, presence of fractures, but presence of fractures, it can be filled with mud filtrate, but not in the whole thickness of the reservoir. The problem of fracture that it is vertical plane, so it will be connected to overlaying and underlaying reservoirs. There might be some cross communication between some oil reservoirs underneath or overlaying this low resistivity pay, and you are testing one of those reservoirs. So you have to investigate why the problem of high production and where the source is this production coming from. Dynamic conditions, we always experience deep invasion. And possibly drilling may induce some fractures. And the directional drilling can be one of the reasons, because when you directional drilling, you are not intercepting the same reservoir thickness as the deviated hole. If this problem happens in an exploration well, the decision to rectify the problem is difficult because you would have to spend more money on what you spent as exploration. Because in this case, you may need to step out and re-drill another hole and take all precautionary actions to avoid the mud invasion and make sure that the mud system is equivalent to the reservoir pressure. A lot of actions would be costly. Most of the time, you are forced to abandon the exploration location. So you are losing a chance. And no one would like losing a chance. You are very close and you quit and go because the management decision is to avoid spending more money and will quit the location. If we look investigating the problem, the conductive minerals, how many conductive minerals we could have? How these conductive minerals could result in such low? Why we are seeing this specifically in this location, not in everywhere? Because if you are in a one reservoir, the positional environment is the same. Reservoirs are deposited at the same time at the same conditions, and they are close. You can find the reservoirs in the Gulf of Suez comparable to reservoirs onshore of the Gulf of Suez. The deep water is almost comparable to the onshore water, onshore reservoirs. There is a comparison always because the reservoir, the positional environment has not changed over those years, million of years. When you say microporosity, we talked about it, how they could hold this immobile water, and by the end, you have some big bores that can produce that much oil. This all can contribute to the phenomena, and this all I would call it a static understanding of the problem. But when you concluded this low resistivity pay, Have you concluded this problem based on static conditions or dynamic conditions? The conclusion was made based on high production rate at surface, without referring to how good the permeability, how big the pores are, but the problem we suffered from that there was no saturation profile. So if you have no, you don't have saturation profile, how could you conclude such a high rate? Fracture and the communicating to stacked reservoir, are they natural or induced? They will lead to the same understanding. They communicate the oil reservoir with a wet reservoir, and when you produce the wet, you can bring the oil up from the oil bearing. This is an example of this low resistivity pay. You can see here the resistivity of the invaded RXO and true resistivity. They are overlaying each other. Whenever you see this overlaying, you conclude one thing, that the deep resistivity is affected by the mud filtrate invasion. And what you are seeing is invasion effect, strong invasion effect. The RXO has a limited reservoir depth of investigation. The RT has a very deep reservoir depth of investigation. So the only time you can see this is invasion effect. So you understand that the problem could you be attributed to mud filtrate invasion. Excuse me. At the same time, you are seeing good match between porosity from core and the porosity from log, which eliminates the possibility of micropores to have its effect on this low resistivity. You have good permeability from the core plugs. Now you are speaking about 5,000 barrels a day, and 5,000 barrels a day, it's related to storage. If you have the micropores effect here, you don't have this much oil storage. So instead of saying high production rate of oil, you should be saying few barrels of oil if the micropores are dominant. So this is another key to understand the problem. There must be a source for this 5,000 barrels a day dry oil production. And you can see here, when you calculate this oil in place, you need area, you need thickness, and you need the saturation. But you don't have area of the pool, you don't have the thickness of the column, and you don't know what is the level of saturation in this oil. So we are not in business. We are losing a very good potential productive reservoir because there is something wrong during the operations that we have to understand and overcome it. Dynamically, if you look at the dynamic data, directional drilling and the logging model. Logging model is designed to be perpendicular to the formation beds. But in directional drilling, it's inclined. So there may be misinterpretation of the reservoir feeding in and the reservoir which is tight, especially if you have shear layers. Excessive mud overbalance and deep invasion is, as we said, is one of the main reasons, and we can see how this could affect your calculated figures of oil in place. Fractures as well, either natural or induced. Investigating the problem, you speak to the geologist, you speak to petrophysicist. Everyone would tell you about static data. The positional and stratigraphically faces the genesis, the core description, open hole logging technique. Is it wireline logging or it is LWG, whatever. If you know how the things with data were captured, you might be able to put your hands on the wrong information. Whenever you have core studies, you can tell how this pieces, how the core samples could tell about the reservoir. You can investigate the whole core plugs, thin sections, the pictures from X-ray diffraction, whatever. You can look at all the data and find out what might be the anomaly in the reservoir. But none of these static conditions would explain 5,000 barrels a day. This is the logging normal model of the logging tools. And this is if you are drilling across a bed. You can imagine how you can misinterpret. How can you be affected by one bed or another bed? This bed is 1 ohm meter and this one is 50 ohm meter. If you are averaging this one, you can be affected by the 1 ohm meter. Could this be one of the reasons? We have to go back and find out how these wells were drilled, how they were logged. This reservoir here, you can see it's low resistivity pay. Top reservoir produced 5,000 barrels a day. But the bottom reservoir was not tested. What are the chances of having these two reservoirs in communication and you tested the top one through a vertical communication with the bottom one? Is it a possibility? Yes, it is a possibility. But unfortunately, the bottom one as well is very low resistivity. So there is a big misunderstanding about this, because actually you might have produced this high resistivity one. This might be the one that feeded in the 5,000 barrels a day. Dynamic wise, the drilling parameters are all are related to mud design. If you are using overbalance and the drilling, they have the right to drill safely. So most of the time they have overbalance. If you are using quite a representative bridging material to stop to create the mud cake and stop further mud invasion. So can we tell from open hole logs? Yes, we can tell from open hole logs. But how much time you need in order to tell from open hole logs that the well was affected by hard mud invasion? We have to be sure that this can be computed instantly and as in short time, because the decision to abandon is very crucial. Pressure gradients of reservoir fluid from pressure formulation tester would help to understand what exactly there. As I said, if you have 0.27 fluid, it does not match by any mean formation water of 0.48. So you are sure that this should be a continuous phase of oil, and this may explain the 5,000 barrels a day. The 100% water saturation, okay, we can understand it's a formation, it's a mud filtrate invasion. Production performance, how those wells were tested. Now this is the tricky part. And most of the time, there would be a DST, open hole drill stem test. And based on recovery, displacing water cushion in the string, they come out with estimated barrels of oil per day. And this is usually extremely high, because if you recover 50 barrels in 10 minutes, you convert the 50 barrels to what equivalent in per day. So that will be a very high number. But in such cases, always we must carry out surface flow production test. Nibble down the Christmas tree, nibble down the BOPs, nibble up Christmas tree, and the production test the well safety through a test separator, providing a long time of production stabilization. You may need to drill a pilot hole. Sometimes if you have in the development well, you have a chance to drill a pilot hole and test this low resistivity pay formation. And the cut and the acquire core and the acquire core material. Excuse me. Later on, if you have this, you can be used as an observer. If in development wells, you can have this low reservoir resistivity pay reservoir cased off, and you can use it as for observation. So you can run saturation logging tools, case load saturation logging tools from time to time to find out if this is a real problem or that was an invasion effect, and by time it will come back, the oil will come back. Here I'm driving one of the cases due to mud filtrate and to mud overbalance. You can see a mud overbalance of 1300 psi. And when you acquire MDT, you end up to a gradient, reservoir flow gradient, similar to that of the mud system in the well, where you are expecting to have oil gradient here, but because you are seeing the MDT, you are sampling only 20 cc. And this 20 cc very close to the high pressure area of the wellbore. So you are affected by the invasion effect here and the seeing wrong picture to what you are expecting to see. So the MDT would help to identify the problem. But you have to control the overbalance. You speak to the drilling engineers to be very careful during drilling this type of formation. This is another example here. This well was drilled, and after 20 years, it was there, nothing done. It was not completed. It was stagnant. And after 20 years, it was completed and produced. So during the time of 5 years, TDTs and RSTs were run in this well. And you can see that the oil-water contact from here moved down from there, and you are seeing high saturation, high oil saturation, in addition to what initially was logged. Simply, what does this say? It says that there was a strong invasion, mud filtrate invasion effect that flushed the oil away from the wellbore. And after 20 years doing nothing in this reservoir, no production, no injection, the oil came back and the heavy mud filtrate segregated down. Luckily, in the same reservoir, another up-dip well was drilled in 40 feet shallower than this well. And the action was taken in order to acquire low invasion core plugs. And these low invasion core plugs used to find out how much the water saturation in the plug itself to verify the log signature. You can see at the top, very good match between the saturation from the plugs. But at the bottom part, when you experience this filtration, mud filtrate invasion, you experience the same effect. Actually, I'm not hearing any. So let us complete, and by the end we can make questions because the seems signals are not that good. So this is the problem I'm speaking about, that you have always,
Uh, Excuse me, Engineer Ahmed. I have a question, if it is
please,
available.
please.
So regarding the chart of core and saturation from open hole log, I can see at the same. No, this chart is the same chart.
This here,
Yeah, this middle one. Yeah,
this
I can
middle,
see at the same, if it is the y-axis, if it is for depth, I can see at the same depth we have a core plug and also the log. And I mean that if it is invasion in the same depth, so I think it will affect the core as well. Correct me if I'm wrong.
uh, this is the whole idea. You are cutting the core and cutting the plugs in a special technique, and
Okay,
not to disturb the initial fluid in the plug. You see what I mean? We are using tracer in the mud
okay,
system. We are speaking later on how this was captured. But you can differentiate between the outside and the inside, where you are measuring the irreducible water saturation or the water saturation in the plug.
okay, okay.
It's a proven technique. And as you could see, you have good match here in the top.
Yes,
But here, because of mud invasion effect, mud filtrate invasion effect, you are seeing the signature of log is drastically affected.
yes.
But initially, it is going online with what you are seeing on the top, a normal profile.
Okay, okay,
Okay, so it depends on how you are cutting the core, what you are looking for, in order to be sure that what you are capturing the information you need.
okay. Good. Thank you.
Okay, so this is the whole idea. In another well, deeper, we have the same problem, and the core data showed mobile oil in the plugs. We cored it and we analyzed it. We find that there was a considerable mobile oil in the plugs. So there is always an invasion effect, because the rock is not homogeneous. You have low permeability, you have high permeability, and if you don't have the right mud to have good mud kick, you always suffering the mud filtration effect. So this one of the main reason attributing up to the low resistivity pH. As I said, if you have good storage, you can see a production sustain. You can see good wellhead flowing pressure. If you don't have that good storage, you can see increase and suddenly you drop on production and losing pressure. So it's very important when you decide on testing a low resistivity pay, you have to reduce it at surface through a production separator, and it's subjected for production testing not less than 12 hours constant rate, in order to see the changes and find out what might be there affecting. But most likely, the reported tested rates were related to open hole drill stem test. The low invasion core is one of the good techniques to understand the real saturation of a reservoir. So you cut the core, but you inhibit the mud system using deuterium oxide or tritium. Deuterium oxide is chemical, it's not harmful, or tritium, it's another radioactive one. It does not exist in the formation. It does not exist in any formation water. It's outsourced, and it's safe to handle. It's not problematic. Deuterium oxide, it's existing in the formation with a ground level of 150 parts per million. So you can design your mud system to be 3-4 times more than that. You cut the core in this, but you cut short cores. Don't wait until you cut 300 feet, because the longer you stay in the hole, the more disturbance you are creating to affect the quality of the core you are looking for. We need to retain the initial saturation of the reservoir inside the core. So we have to cut small pieces, bring it out, one joint every time. And you cut the plugs on surface as soon as possible after taking it. You seal it in envelopes. You cut the plugs here, and you divide the plug to 1 inch from each side, and retain the 2 inches in the core of the plug, and everyone in an aluminum foil envelope, and all kept in an ice box, sealed off and kept in ice box in order to not to suffer dehydration. So you expected that this inner part and this inner part would be affected by invasion, mud filtrate, which would be contaminated by the tracer. This inner part would not be affected by the invasion. Thus, we will not see the high count of tracer in this analysis of the P part, or this middle part. This is the whole idea. You use Dean Stark to isolate this water and find out how much deuterium oxide in each plug. And we have the limit here. Whatever comes below this limit represents the saturation profile. So you can measure the water in the plug, and using the pore volume, you can find out how much water percentage-wise in the pore volume. If it is that part here, which is the level of preparing the mud system, then you are sure that this is affected by mud invasion. If you have to run this one, the owner would be always a reservoir engineer. The geologist doesn't care. He is not worried about this invasion effect. The petrophysicist is not worried about, because this invasion is affecting your reserves. You come out from calculations by a wrong oil in place figure. If you don't know exactly how much this water saturation level, you will come out with a wrong figure of oil in place. So it's your, as I said, it's your baby. You have to take care of it, a reservoir engineer. You have to witness it and exactly do it as you have planned it. The coring mount system, as I said, you can use tritium, which is a radioactive, and there's no, is not existing in the formation. It's safe enough to handle it, or the deuterium oxide, which is very common to use as a tracer. Short interval to core and bring it to surface, but you have the rec time and the coring cost. There is always a budget in this one. Cutting and plugging as soon as you recover it at surface. If you ignore it, this tracer would diffuse inside the core and contaminate all the core inside. So it's useless by the end. When you cut, you have to use nitrogen, pressurized nitrogen, as a cooling media, because nitrogen will evaporate, not water, not oil, because you will disturb the fluid percentage in the plugs. Storage and the cut and the plugs, as I said, you have to keep it in defined aluminum sealed envelopes and in a box, ice box. Monitoring saturation changes by time. These are RSTs in the same well, observation well. You can see this here, invasion effect. After 6 months, each interval here is 6 months. After 6 months from drilling, we run the RST, and you can see that oil is coming back. Another 6 months, more oil is coming back, and so on. Even here, you can see the effect of oil, flushed oil coming back. So the mud filtration invasion effect is very strong phenomena during drilling that you have to control it. You have to discuss with drilling on controlling this invasion effect in order not to lose such commercial proven discovery. Low resistivity weight, we consider it as commercially proven discovery that is no way you can decide on developing it or development. So it's in your hands. When you have it, it's in your hand. It could be real. It could be real, but if it is real, are you expecting to produce that much oil or just a few barrels, not 100 even? Low resistivity pay would not produce thousands of barrels or hundreds of barrels. It can make some tens of barrels. And you would have to artificial lift it. It will not flow naturally. This is all what I have to say, and I'm open to answer any question or any concern of you, please.
Thank you, Engineer Ahmed. And please, if you have any question, I will just share the feedback form. It's very important to validate it. It's just 2 minutes because your valuable comments, we really get much insights from it. And here is just simple reminders of our upcoming CMG. So please, if you have any question, you can directly open the mic and discuss with Engineer Ahmed. I think this is a very hot topic, and we suffered somehow from this phenomenon in our fields. So if you have uh, any experience you want to share, any key lesson, any advice, any recommendation, any question, I think Engineer Ahmed, we are all ears.
Please shoot.
I'm sure all Engineer Ahmed, we want to show our deep appreciation and thank you for your effort and your time, actually.
Thank you very much, Upa. Actually, Karim, when he touched me for this webinar, he left it up to me to choose whatever subject I would like. And I found that low resistivity pay is a real concern in the industry, that people don't give it that much attention about investigating why the problem is there. Because the problem, you could lose very good reservoir if you experience it in an exploration well and you quit that exploration without any further investigation. So I hope the subject is as interested for you as is interested for me.
Yes, actually, it was very interesting. And earlier, as I discussed with you, Engineer Ahmed, about our GAPCO fields, that we already encountered some of these low resistivity, but let's say it's by luck or by it was just like a last trial for one of the wells, and it actually produces. So they began to re-evaluate, as you mentioned, began to recall the logs and recall the PLTs, RSTs, and also if there is some cores. I'm not sure if cores were treated the same way you mentioned or not. But يعني I'd have to say that after this re-evaluation, around 3 wells were put on production from some low resistivity layers and already produced oil.
So as I say, your key to identify these wells as low resistivity pay is the production rate. Am I right?
Yes,
So
yes,
this is what deserves to look at first. How this was tested, how long was tested, and can we repeat the test and find out how long we can sustain it? Because if it is a low invasion effect, it will take time to segregate and bring that
yes,
flushed oil back again. But again, time-wise, you can compare time 2 to time 1, time 3 to time one and find out that this is enhanced. It's not only one time tested, and we have no idea how this was tested, how long could sustain production, because it's very important to sustain production.
Okay. So I have another question regarding the NMR. If I have this option, would it help me to allocate or to define the low resistivity zones, or it will be misleading?
No, it will not be misleading, but NMR, are you applying any NMR in every well?
No.
Okay, how can you relate well X to well Y and Z and the M and the N?
Okay.
Okay, we are just running NMR to check what
Okay.
might be the case. But when you come to reality and you need to compare X, Y, and Z, and the N and the M, you have to have fair comparison.
Yes. Yes. Yes.
This is why we are using open hole logs. We are, if you look at the open hole logging program in your company, you will find it almost standard.
Yeah.
It's the
Okay.
same tool, it's the same condition, everything is similar. So you can have a good comparison, static and invasion wise, if the invasion
Okay.
experience in one well from the another well.
Okay. Great. Great. I think we came to an end, and I think there's no more questions. Again, if anyone have any questions, so feel free. But I can see that the same attendees, and I think no more questions. So it's an end, and thank you again, Engineer Ahmed, and
You are
hopefully
welcome.
we'll have more webinars in the future, inshallah. Thank you deeply. Thanks a million, and
Thank
thank
you.
you all for attending.
Thank you, Opa. Thank you, everybody. Have a nice time and enjoy.